All right, the next thing we're going to talk about is the comparison theorem. The comparison theorem is going to be our main tool for determining whether or not an improper integral converges or diverges. Something that is a little bit strange, maybe not strange, but it's a shift in what we have been used to doing, is the comparison theorem simply tells us whether or not an integral converges or diverges. It doesn't actually help us find the value of it. It might allow us to, or it might provide a suggestion or a hint as to how we might estimate it, or provide a bound. You know, the value of this convergent improper integral is between this value and that value, but in and of itself, it is not going to, we're not looking for the numeric value. For these next few questions, and as we move into series, we will simply be interested in, does this thing converge, not to what value does it converge. Sometimes we might be able to figure this out. In other instances, we might not be able to. And many of these questions are not phrased that way. Many of them are just asking yes or no. Does it converge? That's it. So for the comparison theorem, at the bottom here, theorem 3, we essentially are taking a look at two different functions. A function called g and a function called f. Their names aren't important, but what is important is that one of the functions is sandwiched between 0 and the other function. So I'm going to call, this function, sure, its name is f, but we can think of this function as the bigger function. And we can think of g of x as the smaller function. So the main idea behind the comparison theorem, there's two statements. Let's take a look at statement 1 first. So statement 1 essentially says, if you have two functions, one is bigger than the other. So here is a function f. Let's say there's f. And then we have a function g, and maybe g does something like this. Maybe it goes up a little bit, maybe it touches f, but it's always less than or equal to f, and it's always greater than or equal to 0. So there's g. So if we know the area underneath the graph of f, if we know this area is finite, then the area in blue, since it's less than the area in red, well, that also has to be finite. So if the area underneath the larger function is finite, then the area underneath the smaller function must be finite. And then the argument works in the reverse way when we take a look at divergent integrals. So if the smaller function, if the area under the curve of the smaller function is infinite, then the area underneath the larger curve is infinite. That's essentially our argument. Okay, let's take a look at this example 9. Determine whether the following integral converges. So notice here that what's missing is the follow-up statement, if it converges, find its value, or find the value to which the integral converges, provided it converges. So in this case, we just simply want to say converges or diverges. So what we're going to do here is first notice that we are going from 1 to infinity. So this means we are integrating over an unbounded interval. So this is a big interval. Okay? Furthermore, what we have here is an expression, our function, is not a P integral. So there's really two options that we have here. Option one is to just begin integrating this as we would directly and using a limit. So the limit as r goes to infinity, the integral of 1 to r, and then we can split this up into 1 over x plus x to the negative 3 dx, and we could go ahead and integrate this natural log of x, absolute x, and then this would be minus a half x to the negative 2 between 1 and r, and go from there. But that's a lot of work, and we also, well, we're not asked to figure out what the value is. But then again, if we find out the value and it's not infinity, then that means it converges. So this is a valid way of answering this question, but it's a little bit more work, and it's not going to be using the comparison theorem. Now, this question doesn't say to use the comparison theorem, but this is really where the comparison theorem is convenient. So let's not do it that way. Let's take a look at how we could use the comparison theorem. So essentially, we need two functions, two different expressions. One of the expressions has to be the expression we're given, so the integrand of our given improper integral, and the other expression is something that we are going to find or build or construct. Does it really matter how you find this function? Not exactly. It could come to you in a dream. It could be divine inspiration, or it could just be an algebraic sort of, derivation. Could be something that you just constructed using inequalities. But what's really important here is the fact that we do have two expressions, and we know how they're related. We know which one's bigger than the other. And for the comparison theorem on the previous page, we do need them to be positive functions. So take a look at that. So what we'll do is we will pull out our integrand, x squared plus 1 over x cubed. Now the first thing I'm going to ask myself, okay, is this positive? Is it positive? Yeah. Think about our x values here. The bounds tell us all of the values for x, all of them, that we're going to see or feed into this expression. Well, we're only feeding into this expression positive numbers. So this has to be positive because we're not subtracting them or doing anything else to them. We're just adding and dividing. And if we're only adding and dividing and multiplying positive numbers, the result must be positive. So I can just say that is greater than 0. We don't have to give any more of a dramatic explanation or justification other than just writing that inequality down. Now, what we do know is we either would calculate this directly, as I started to do a few minutes ago. That's one way to find out if the integral converges. The other way is to compare it to a function whose improper integral we readily know or readily can see whether it converges or diverges. So a quick, convenient thing that we could quickly check. Does this converge or diverge? So our goal here, really, the unspoken goal, it's not literally this, but a rule of thumb or a good strategy. So a good strategy is to compare to p integrals. Because we know very quickly by looking at a p integral whether or not it converges based on whether we're integrating over a bounded interval or an unbounded interval, and whether our value of the exponent on x, the power p, whether it's greater than 1 or less than 1. Those two things immediately can help us determine whether or not an integral converges or diverges. So we will try to build a p integral from this expression. So remember, a p integral is something that looks like this. the expression is 1 over x to the p. So this expression here, how could we slowly try to change this so that it looks closer to 1 over x raised to some number? Well, one thing we could do, so this is just, a thought bubble here. If I have x squared plus 1 over x cubed, what I could do is it would be really nice if this 1 weren't there. If that 1 weren't there, then effectively I'd have to take it away. So if I take away that 1, now I know that this is not a legal move algebraically, because you can't just delete something from the numerator. But what I could say here is if I were to get rid of that 1, then this would be x squared over x cubed. So the only difference between this numerator and this numerator is that this numerator here is bigger than this numerator here. Well, if you have two fractions and their denominators are the same, they are equal, and the only difference is the one numerator is larger than the other, then the fraction with the larger numerator, is a larger fraction. So the inequality symbol we would need between these two things is the greater than or equal to symbol. So I'm going to reproduce this over here. Well, actually, let's go back for a second to our red thought bubble here. Let's simplify this first. X squared over x cubed is 1 over x. So that 1 over x is what I'll import here. Now these inequalities here and the equality, they are transitive relations. It's a transitive relation. So that means if this expression is greater than or equal to this expression, and this expression is equal to this expression, this means, transitively, that this expression is also greater than or equal to this expression. So this right here is just sort of like an intermediate step. It was useful, but it's ultimately not what we're going to carry over into our final work. So here, I'm going to go ahead and just say that this expression here, I'm going to have to move that. It's greater than, so my greater than symbol, I get right here. Now, if you insert something in the middle of an inequality, you just want to make sure that the order in which you inserted it actually makes sense. So is this 1 over x actually greater than or equal to 0? Yes, clearly, since we're only plugging in positive numbers for this x. So this inequality is good. It's true, it's valid. So now, what we can do is say, hey, this function right here that we have, this is a p function. So if we actually take a look at its p integral, we should be able to then use the comparison theorem. So I would write it out like this. Since, sort of like a mini proof, since this inequality is true, and the integral from 1 to infinity of 1 over x squared, 1 over x, I should say, 1 over x diverges. Why does it diverge? We can say this is p equals 1. It diverges, that's our justification. By comparison, so must the given integral. And that is our solution. So in the case of these comparison theorem problems, you really should be writing down some sort of miniature proof, something, a first or second order formal proof. It's small, but it has all of the correct elements of just making a little argument. So in particular, what you need for comparison theorem is you need to satisfy the hypotheses of the theorem. So hypotheses of the comparison theorem are that we have two functions, and they are each greater than or equal to 0, and one of them is greater than or equal to the other. Okay? So this is really what we need. So we have to, in order to use the comparison theorem, we have to identify this inequality. So we need an inequality, and then we have to make a statement about the integral of the one function and how it relates to the integral of the other. So coming back over here, we have our inequality, check. So we've shown not only which function is above the other, we've also verified that they are both greater than or equal to 0. So then we're going to say, okay, the integral of the smaller function diverges, so by comparison, the integral of the larger function must also diverge.